I'm Anand Buddhadev, and I'll be chairing the session for this afternoon. I hope you all had a good lunch. We're going to start off this afternoon with a couple of announcements first. I'd like to thank our sponsors for DNS-OARC 31, Comcast. I would like to remind all of you to please fill in the survey. The link is in Indico, and I've been told that if you experience any glitches, please try again in a bit. They are being fixed. And finally, if you would like to go to the social this evening, there are still 15 or so tickets available, but you must register before 3:30 p.m. So please do that ASAP. And with that, we're going to start off with the first speaker for this afternoon, who is Austin Hounsell, who's going to talk about the costs and benefits of DNS, DOT, and DOH for the modern web. Welcome, Austin.
Hi, I'm Austin from Princeton University. I've given this talk a couple of times now, I think at NRW, NANOG yesterday, and RIPE, so I apologize if this is something that you've seen a couple of times before, but nonetheless, excited to present it today, and thank you for being here. So I don't think I need to say this to the room, but we know that DNS privacy has become a significant concern, with now major browser vendors offering to implement it. And we're seeing today with the likes of Comcast that even ISPs are starting to take it up. And we know this because that is a problem because on-path network observers can spy on traditional DNS traffic. I'm going to refer to traditional DNS as DO53 for the rest of this talk. And so there's been two protocols that have been proposed to encrypt DNS traffic. There's DNS over TLS or DOT, and DNS over HTTPS or DO, as I'll refer to these protocols for the rest of the talk. So what we wanted to do is understand, from the perspective of an end user, what is the performance of DO53, DOT, and DO, not just in terms of query response times, but also page load times, and if we were to traffic shape our network to what we believe some cellular conditions might look like, how does the performance change? If you're taking your cell phone around and you're on like a 4G network or maybe even a 3G network, how do DOT and DO affect page load times? And we performed these measurements from 5 different global vantage points that were all hosted on Amazon EC2. So today, because we are in North America, I'm going to be focusing on some results that we did from the Ohio region. And in our paper, as a preprint, we have some data from the likes of Seoul and also in Sydney, Australia. So the most unexpected finding that we had from this research was that despite higher DNS response times, we found that page load times with encrypted DNS transports can actually be faster in some cases than DO53. Which, again, was not something we expected at all coming into this research. So I'll give some reasoning of why we believe that might be the case and how this might lead to further research. So we're going to start off with just DNS response times. So these are just showing the DNS response times for when we use Cloudflare with the Ohio Amazon EC2 vantage point. And so you can see by the legend at the bottom that we're comparing not only Cloudflare's implementations of different protocols against each other, but also with the local DNS or DO53 resolver that was provided by Amazon. And so there's a couple of interesting things we can take away. It's not only the case that Cloudflare's DO53 resolver can be faster in DNS response times than the local resolver, but we also see this interesting behavior where DOH is initially slower in terms of DNS response times than DOT, but then it manages to catch up at a certain point. And we also see that, kind of in the tail of these response times that DOH and DOT catch up to unencrypted DNS or DO53. And just to make a note that this legend at the bottom is showing just the first 250 milliseconds of response times. The smaller plot, which has now been taken up by my text box, shows the full 1,500 milliseconds of response times. So we see that, early on, that although DOE starts out slower and DOT starts out slower than traditional DS, they manage to catch up. And so this is showing the same thing whenever we use Google's recursive resolver. So we see slightly different behavior where DOH seems to be performing slower for a longer period of time than DOT and DO53. But nonetheless, we see that they managed to catch up a little after, maybe 250 milliseconds, that in terms of response times, DOE is catching up. And lastly, this is with Quad 9 at the Ohio EC2 vantage point. So again, we're seeing that DOH is catching up by about 200 milliseconds. But we see this interesting behavior with DOT, where the response times seem to be significantly slower. We weren't exactly sure why this was the case. We've reached out to Quad 9 and having some ongoing discussions about not only our source code, but also how we could explain these results and try to improve them. So again, you're seeing that DOH is outperforming DOT for almost all queries in this case. It's not just later on in response times, it's very early. And you also see that DOE is catching up to DO53 at some point in time. So the kind of takeaway from this is that DOH just has a overall higher mean in query response times, but a significantly lower variance. And this was a result we observed not only in our Ohio vantage point, but across all 5 of our EC2 vantage points. And there are several possible explanations for this. One is simply that providers like Cloudflare are able to cache DNS responses very close to the edge and closer to the users. And there might be some complex layering of HTTP caching interacting with DNS resolver caching, which might improve response times. And it might also be the case that some wire format caching is going on with HTTP, which is enabling DOH response times to be slightly faster. We don't have any measurements of exactly how much that could be improving it, but this is something that we hypothesize might improve response times. Again, by being able to use HTTP, you might get some extra performance with DNS response times. And so again, as I previously mentioned, we also wanted to emulate different network conditions, particularly poor network conditions. If you were to perform traffic shaping with additional latency or packet loss or add jitter, we wanted to see what would happen when you use these different protocols in terms of query response times and page load times. And the reason why we are motivated to do this is that we see that DOH and DOT, or DOE and DOT, are starting to be offered on phones, whether it's Cloudflare with their mobile app or Android 9 supporting DOT. We think it's important as we talk about DOE and DOT performance to understand, how are mobile users going to perform when they use these protocols. And again, as mentioned, the performance might be significantly different. So we didn't perform measurements on real mobile phones. We could have tethered, but rather, for the sake of being able to scale up our measurements across EC2, we wanted to just emulate different network conditions based on some data that was provided by an open signal report about how much additional latency are you getting when you use 4G, if you were to use 3G, and so we use those numbers. And so these are 2 CDFs that compare differences in page load times between protocols within Cloudflare. And so again, this is focusing on Cloudflare at the Ohio EC2 vantage point. And so the way you can read this is that if you take, for example, on the left graph, you have Cloudflare DOT minus Cloudflare DO53. This is comparing page loads for a given website across all of our websites between DOT and DO53. And so what you're seeing here with the vertical line in the middle, which is representing the median difference, is that DOT was about 1 millisecond slower than DO53 in the median page load time. Again, this is without any kind of traffic shaping. These are just on default network conditions on EC2. And I should also mention that we measured essentially the Alexa top 1,000 and then the bottom 99,000 to 100,000 websites. And this graph is showing those measurements put together. We were interested to see not only how do DOH and DoD perform on really popular content, but also less popular content. And you're seeing some somewhat similar results with DOH. It is slower than DOT, where the median page load time is only 19 milliseconds slower than DO53. So you are seeing that, there's this kind of ordering of DO53 is faster than DOT, and DOT is faster than DOH in the median page load time. So this is what happens when you go to our 4G settings. So again, we have these numbers provided by an open signal report where you do traffic shaping with an additional 50 milliseconds of latency. You drop 0.5% of packets, and you have 8 milliseconds of jitter. And so you're seeing that DOT still manages to keep the same performance with about, now it's 1 millisecond faster than DO53, but DOH is now 70 milliseconds slower than DO53 in terms of the median page load time. Something else I should note as well is that we are reusing the TLS connections when we're doing DOT and DOH. And then here we see some even more interesting behavior on what we call the lossy 4G setting, where we reused the same latency that we traffic shaped with, an additional 50 milliseconds and 8 milliseconds of jitter, but now instead of dropping 0.5% of packets, we're dropping 1.5% of packets. So you see this really interesting behavior where now DOT was 62 milliseconds faster than DO53 in the median page load time. And now you also see that now DOH is 20 milliseconds faster, which again was a really unexpected result for us, as I mentioned at the beginning of the talk. And so in a couple of slides, I'll give a hypothesis that we have or why this might be the case. And then everything kind of collapses when you go to the 3G settings, which is about, I believe, 150 milliseconds additional latency, 2.5% packet loss, and 8 milliseconds of jitter. So you're seeing that DOT is now about 200 milliseconds slower than DO53, and DO is 260 milliseconds slower in the median page load time. So, why do we think we see this unexpected behavior where depending on when you go to lossy network conditions that the performance can actually be better? So we think it has to do with differences between TCP retransmission times and UDP, where the TCP packets can be retransmitted after 2 round trip times, whereas the timeout of DO53, the UDP timeout, is set to 5 seconds by default in Linux with resolve-conf. And so we think that if you're on a lossy network that isn't too lossy, it might be the case that you're able to retransmit these DNS packets faster than you would over an unencrypted transport. And so we think this speaks to further research that needs to be done on comparing, for example, DNS over TCP and seeing how that would compare to UDP on its own, which is some ongoing work that we're doing. So, just to summarize, we just wanted to compare DO53 DOT and DO performance from 5 different EC2 vantage points. For this talk, I only showed one just for the sake of time. But in future work, we want to scale up our measurements to real residential ISP networks. And we have some ongoing discussions to do that, to see, from the perspective of, a real customer, what does the performance look like? And we also are interested in performing some measurements from networks that are further out from CDNs. For example, there's some colleagues of ours in Cape Town in South Africa, and we're working with them to scale our measurements to further away regions and see how these protocols perform. That's all I got, and I'll take any questions, and thank you for listening.
So I have a couple of questions and remarks. So you did that sort of testing out of Amazon, so a virtual platform,
Right.
And then compared the local resolve that probably also is in a virtual platform against something that is running probably for a Perform network.
Correct.
You know that UDP and TCP perform very different when it's kind of virtualized stuff.
Okay.
So that's something I think you need to take into account when you do further testing. Then can you show me the first, I think the first graph where you have this kind of page 4, yeah. It's like-
All the way back to 4?
Oh, yeah. So,
Sorry about that.
so that means that sort of, no, that was okay.
5?
This one, yeah.
Okay.
So that means that on the probability means that until you reach that kind of where the time is the same, is 80-90% of the queries are to the left, right?
Correct.
That means most queries, and then the other I think it's even more pronounced, are faster with the regular
That's correct.
thing. So the thing that is, if it goes beyond 200 milliseconds, that's the bad guys, the long tails. You don't care about that. So, I mean, out of that saying that the response time of DO or DOT is faster, for these cases, that's not the user case. I mean, the real thing we need to test are the browsers at sort of the end users. And I think there was a test from Sam Knows that they are testing behind actually the CPE.
Right.
And that showed various different results. So.
Right. So that we're actually in discussion with Sam Knows to kind of scale up our measurements. That's part of what we're doing. Speaking to this, like working with residential ISPs to do that. But something that would definitely come out of future work that we want to see is just if we were to put these measurements close to like the end users, how would it perform? Which I think you're speaking to as well.
Just a quick announcement before we continue with the questions. A reminder to everyone to please announce your name and affiliation when you come to the mic. And there's a slight change in the agenda for this afternoon. So Jesse and Carl are going to be presenting next, and we've moved Professor Shuang Hao's presentation to the end. So Jesse and Carl, please prepare yourselves. Jess, Jared, please continue with the questions.
Thanks. Hi, Jared Mach from Akamai. I think it was slide 14, 15. You were talking about the resolve.conf settings of the 5-second timeout.
Right.
So I'm curious whether or not you're intending to repeat this by reflecting, I think, maybe a more modern setting for timeout of closer to maybe 1 second, because many of the, like DO53 from, I think, OpenDNS, it by default responds at 1 second, even if on the backside it wasn't able to get a response.
Okay.
And so I'm curious what impact that would have in the studies for your simulated cellular and packet loss environments as well, because most RTTs are less than 1,000 milliseconds on the internet, and I'm curious whether or not you're intending to repeat that as part of this here.
Yeah, I mean, just to give a little more detail, these are measurements that we carried out on, we are running Debian just by default, and so like it would definitely be interesting to see how this would work with different timeouts. That's kind of like an additional next step for us as we test with just DNS over TCP to kind of tease out this performance a little more.
Yeah, because I think there's probably probably guidance to operating system developers and what those timeouts should actually be, because it's entirely possible 5 seconds is probably too long,
right?
For 2019, 2020 timeframe.
Sure.
Thanks.
Wes Herdeker, ISI. Following up on that, I actually did a study 15, 20 years ago looking at the comparison of UDP and TCP in lossy networks, just like you did. And what I found is that most, the application that I was working on at the time wasn't DNS, but with a 1 second timeout, it looked slower, except that as loss got worse, TCP actually started suffering at some point. In fact, eventually TCP would fail and UDP would win.
Right.
But what I actually found is that if you were intelligent about picking your timeout, like if I knew I'm always talking to this thing and it's always typically responds within so much time, if I multiply that by 1.5 and retransmit it on a faster rate, in other words, an intelligently derived timeout flattened TCP entirely. So I suspect that your current results are correct on a lossy network, but we could probably improve on the UDP side.
Sure. Thanks a bunch.
David from Alibaba. And one slide, you're talking about the cache, right? You guess there may be some impact from the cache. I wonder what's the method you use to launch the DO query, because there are two methods, get and post. So I would like to ask, which method are you using? I guess it's get, right?
I'll have to go look back at that. I don't remember off the top of my head, but we could talk offline, and that should be something that's trivial for me to look at.
I'm sorry. I just want to ask which method you send your DO query, because
Right.
you can use GET, that will be cached in the middle. And if you use POST, it will, right? So my question is simple, that do you compare the different?
Did we compare the different methods? No.
Yeah.
We just measured with one. I don't remember which one it was off the top of my head. I would have to get back to you offline.
Okay, because there are different, the payload size is different, so I guess there may be some impact on the data you
Sure.
receive.
And just like as an additional detail of our DO setup, we used HTTP 2 as our configuration, but I'll have to get back with you what method we use off the top of my head.
Victor Duchovny to Sigma. My question is really around tuning the connection reuse and TLS session caching and all of that. I'm not seeing much guidance in any of the published documents about how you should, what the best practice is in that space.
Sure.
Have you looked at the impact of changing the lifetime of your TCP connections or TLS sessions?
No, so we stuck with the default timeout. So what we'd use for DOT was stubby, and the default timeout of stubby was, I think, 10 seconds or 10,000 milliseconds. And so that was the timeout that we had used across all of our measurements.
Right, so you keep a connection alive so long as there's ongoing
Right,
traffic.
essentially.
And then, of course, in a survey, you have artificial loads. You may be keeping the connection alive for a long time because you're constantly making queries.
Right.
It may not mirror what an actual
Right,
user
like if
would
a
do.
user had stopped browsing web pages for longer than 10 seconds, then they
Right,
might
and
have to
then
open a new
click-
connection.
Right, was busy reading and then resumes browsing.
That was something that we thought about as we were designing the experiment, and we weren't sure really how to model that. So just for the sake of simplicity, that's what we had stuck with, just using the default 10-second timeout
Right.
and replicating that across our
It would be
measurements.
good if you could actually somehow, I don't know how, but come up with recommendations based on measurements as to what appropriate
Sure.
session lifetimes are.
Yeah, that'd be something great to look into. Appreciate that.
Hi, hi, Puneet from Google. Couple of comments. One on TCP, what Wes Hardaker said. I think there's also these days a new version of TCP for congestion control called BBR.
Okay.
So I'm wondering whether you have played with that, because it adapts better to packet loss than the default TCP implementation. So it'll be interesting to see results with that.
Okay.
And on the other point, I think we as a DNS community, we're doing a great job measuring DNS. But one of the concerns I have with us going very deep on measurement here is, especially for browsing, is that most of the time is spent in the browsing, loading all the ads and all the rich media on the page. So we should keep that in perspective. Losing 10 milliseconds to gain privacy or better DNS, I think is a reasonable trade-off if your DNS is protected, when the page itself may take seconds to load. So I think we should always keep that in mind. So what I would suggest or request you is that when you put up the numbers for DNS measurement, you should have something which gives a relative DNS contribution to the overall latency of the page. So we can say if DNS is taking 200 milliseconds and the page load is taking 5 seconds,
Right.
so it's in perspective.
Yeah. Thank you. That's definitely something we can do. Good. Thank you. And if anybody wants to speak offline, I'll be around. So thanks for listening.
Thank you very much, Austin. Before we move on, I have an announcement. If anyone wants to submit any lightning talks, please do those using Indico so that the PC can consider them. I think we've already had a few submissions, but if you're thinking of, please do that now. The other thing is that we have a change in the schedule. We're moving up Jesse and Carl's talks, and so they're going to present now, and then Professor Shuang Hao's talk will be the last one for this afternoon session, and that session will not be webcast, So we will be cutting off the webcast after these two presentations, and that's because the speaker has requested that it not be broadcast, and the PC has agreed. So for those who are listening in remotely, please note that the webcast will be cut off after the following two presentations by Jesse and Carl. So first, I would like to invite Jesse Kipp to the stage, and he's going to talk about DOH preference hints. Welcome, Jesse.
Hey, I'm Nick Sullivan. I'm co-presenting.
Hi, I'm Jesse Kipp. We're both from Cloudflare.
Okay, so this is a statement that may or may not be true. Maybe not everyone agrees with it, but it seems to be happening. So DOH is coming to a browser near you, and browsers of various sorts are starting to use DOH, and there are multiple deployment proposals for how they use it. One proposed model is that of opportunistic encryption or opportunistic upgrade. Specifically, if the system resolver itself does also support DOH, then DOH would be used with the system resolver. Another deployment model is to use a single privacy-preserving DOH server, and this is something that's been pre-configured and pre-vetted into the browser itself.
So the model we're moving here to potentially is one in which there's multiple DNS servers potentially working within to the application or the system to resolve lookups, and there are some potential downsides to using a single fixed resolver to resolve all DNS queries. One is for performance. A large network or CDN cloud provider may be able to perform faster resolution for particular websites where the server is co-located with the DNS, for example, or the authoritative is co-located with the resolver, rather. There are potential privacy reasons that spreading DNS queries across multiple resolvers conceals the full browsing history from a single provider. There may be security considerations. A site may want to recommend to its users that it use a resolver that meets specific requirements for security or functionality. And there may be commercial considerations where there may be real or perceived pressure for resolvers operating to respond to queries for different properties in different ways, faster or slower, and so on.
Right, so if we kind of sketch out what these future proposed deployment models of multiple resolvers known by the application look like, one potential model here is rather than a single trusted DOH resolver, it's a curated list. There's also potential for discovery to happen, so the application itself to find a list of designated or trusted DOH providers and build a list of these. And so in this new model, the question is for a given query, which resolver should the application use? If you have a preset list or discovery, these are the sort of sets of resolvers that are optional or that are potentially used for queries. And there's a number of different resolver choice mechanisms. One could be just your standard round robin, pick a different resolver based on random choice. And then there's also the possibility of having some sort of sticky associations in which having resolved a DNS record one way, it may stick in one way or the other. So the downsides of this specific preset list and round robin are similar to that of applications having a single DOH resolver, for, one of which is performance. It may be less than optimal to choose one resolver over another. If you're looking for the fastest possible performance, round robin just sort of spreads it out between all of the different resolvers. there's also some privacy consideration as well. So some, as mentioned, some DOH servers are co-located with authoritative servers, and this is a naturally attractive privacy property to have. It prevents the query from being spread to multiple organizations. Doing round robin does not take advantage of this.
So a proposed solution that we've put out as a possibility here is a response header that comes back from the server after an initial HTTP response to a page load, indicating what the preference is for the future resolutions of that domain name to be done. So the idea here is that it's inspired by HSTS, and the preference is completely optional. The user agent is free to decide whether or not to take this preference hint in the future. So the intended deployment here is that browsers would ship with a vetted list of servers that meet the requirements of that application for privacy, security, and so forth. And then there's some discovery method for figuring out what resolver to choose for a particular domain. So initial resolution isn't addressed by this proposal, but the future subsequent resolutions of that domain are. So content providers can supply a hint, and if the hint is in the vetted list, the browser would use that resolver in the future. So first request, browser uses its default resolution mechanism, gets back a hint about future resolutions. Subsequent requests, if they're within the age time limit of that header, are resolved from the preference at the resolver specified in the preference hint, and then the site is resolved. So this addresses a few of the issues, potential issues with a single resolver. The origin potentially knows the fastest DOH server for its host. The origin knows which resolver potentially can be trusted with its queries. The origin can choose resolvers that have a higher level of security, such as DNS-SEC validating. And the origin knows potentially which resolvers have potentially commercial conflict with the site itself or with other service providers, network providers. One thing to note is that unlike HSCS, the fallback is always to default DNS resolution mechanism here. The trade-off is between losing access to the site entirely because you're unable to resolve versus gaining the advantages. And we feel in this case, fallback should take place to the default resolution mechanism. One other thing to note is that there's a potential for tracking here that needs to be addressed. And there's both a direct tracking mechanism that needs to be addressed where it would potentially be possible to issue a unique DOH URL to every client. And so the URL needs to be vetted against the list. And then there's a side channel where the value of the hint has to be cached by both the browser bar origin and the resource origin that's being fetched, so that resources can't learn about whether, sites can't learn from fetching a resource whether another domain has been visited and cached. Thank you.
Thanks. Any questions, please? And please remember to identify yourself.
You said vetting a lot. I mean, do you really believe that it is possible with thousands or hundreds of thousands of people doing apps and doing stuff like that? And I mean, all this resolver stuff is taking away the security mechanism that people have built into DNS over years and that they are using to protect the network. I mean, it wouldn't work with an enterprise. I mean, I don't think this is a really good idea.
So I guess the question here is how many potential trusted resolvers are there and how are they discovered? And this is something that boils down to the browser's choice of policy here. And we are making the assumption that the browsers that have decided to tackle DOH and do so in the public internet realm, not rather than potentially the
Well,
enterprise realm.
But browsers get used everywhere, and you cannot, and even within the sort of public internet realms, there are people sort of using that, and there was, in the earlier talk, to deliver security service over DNS, and you are trying to circumvent them, right? So, and the vetting, okay, you said browsers do that, but it is really doable in today's internet world with millions or billions of participants to do something that we can vet a list. Don't we need sort of an automated mechanism for that? And that's not possible for that.
Yeah, I think that's outside of the scope. We're assuming that the browser vendor, specifically Firefox, are going to do that. And this is to address challenges if they choose to do that.
Robert Edmonds, Fastly. I think you had a slide up there with the example of the parameters like max age. I think the value you gave was like 6 months. Was that correct?
I don't remember exactly, but yeah, I put it pretty long. Longer definitely than the TTL of the record.
So, not just the TTL of like the address record, but the, like most TLDs have like a 1 to 2 days seems typical. How, isn't that max age, shouldn't that max age be capped to like less than a typical delegation TTL?
Yeah, I think we put the too long of a date just to demonstrate the similarity with HSTS, because that's the sort of timeline that HSTS has done. But yes, I would suggest that this is much smaller scope than 6 months.
Okay, and my other question was, it seems like there's an implicit cross-protocol delegation occurring. Is there like an explicit justification for that?
Not particularly. I think a lot of policies being set in HTTP apply beyond HTTP itself. HSTS is the canonical example here, so this is following in that tradition.
Okay.
Hi, Puneet from Google, but I'm speaking without my Google hat on right now. I think for something like this, which is proposing to provide some privacy benefits at the cost of introducing complexity in the serving infrastructure, I think it needs a cost-benefit analysis section also, because in my mind it's unclear whether the benefit provided here is worth the complexity it's going to introduce.
Hi, Vittorio Bertola from Open Exchange. Sorry for the non-technical question. Maybe we can follow up later. I was just curious if this was ever discussed with your policy or legal people, because I see it very hard to make it compatible with the GDPR data protection model, in which users have to consent to send data to a new entity every time this would maybe get proposed by a website or so.
We can talk offline.
Okay. Jared Mach at day job, I'm Akamai Technologies, but I'm asking this as a small fiber to the home operator. So I happen to provide internet access to a bunch of my neighbors, and including my family as well. And I'm wondering how you're going to vet me as a provider of a well-qualified service, because there's thousands upon thousands of service providers, and this seems like something that you're going to be unable to do at scale. And also, I've previously done the Open Resolver project, and there's millions of resolvers out there that answer DNS queries, including ones that are either well-configured or moderately well-configured or whatnot. I'm wondering how you're intending to qualify all of those as well when they upgrade their software and have either DO or some other capabilities.
Yeah, so this question was hinted at before, and I would say that it's sort of assumed to be a precursor to this, that the browsers themselves have proposed that they're going to be doing some vetting mechanism, and this is predicated on that happening. So whether or not that's something that can happen or not, it's a presupposition for this.
Yeah, I'm very concerned that we're putting a lot of effort into this, and it's not something that will scale. We've had a hard enough time keeping track of the CA authorities and what they can actually issue, and we're talking about something that is orders of magnitude higher in scale. And I'm afraid that the people who are developing web browsers and trying to do this, I think their motives are pure, but I think that they underestimate the amount of effort to communicate, especially when a lot of the publications are in English and not well accessible to the international community. Thanks.
Yeah, thank you for that point.
Brian Dixon, day job is GoDaddy. I think there's a fine point in some of the documentation or the assertions that have been made by Google Chrome. If you go back to where their deployment policy is listed, like I think it's the first or second slide. So technically what they've said they're going to do is if the system configured resolver is DOE and it's on their list,
And
which is
embedded
very
list, yeah.
different.
Yes, yeah, that's true.
Yeah, and that list is not long. So I think that is something that maybe needs to be corrected wherever it occurs.
Yep, that's a good point. This is a correction for the slide. Thank you.
Yeah. The other thing, sorry, just to follow up on Jared's thing, I think that gets to the crux of the fact that there's already been some research done that says there's, of all the things that are seen in terms of resolvers, or things that could be resolvers, there's about, of those, which are in the many millions, about 3 million are actually resolvers. And that definitely speaks to the lack, or the change to the diversity in resolver usage when that gets highly focused, highly concentrated. And I don't think that's a good thing. Anyway, thank you for the...
Thanks, Brian. I'm afraid we don't have time for any more questions. Sorry, Robert. So thank you, Nick. Thank you, Jesse. Right. Apologies for that. But we didn't have any time for any more questions. Next up, we have Carl Henderson, who is going to talk about considerations to operate authoritative DNS over TLS. Welcome, Carl.
So this is my little clicker. Can everybody hear me? All right, so you can probably see from my red lanyard, this is my first time to OARC. I'm happy to be here. I'm also happy to be back in Austin. I went to school here about 35 years ago, so it's good to be back. It's changed a bit, and it's a little colder than I recall it. So suffering through that with the rest of you. So DNS encryption's been in the news a lot lately. It's been very controversial. I don't want to be in the news, so hopefully I'm going to make this boring by talking about what authoritative operators need to consider when implementing DNS over TLS. Is this my little clicker? How do I get it to advance, guys? Thank you. The one with the big arrow on it. Okay, so the IETF's been working on a body of work for a while on what the communities come to know as DNS privacy standards. So looking at a timeline of this, we'll start off by looking at TLS 1.3. That was a draft in 2014, although technically this isn't a DNS encryption standard, it's a big enabling technology. Then the RFC 7258 came out and declared pervasive monitoring as an attack. So this is of interest to the DNS community because it's traditionally unencrypted. The Deprive group was also formed in September of 2014. This is the DNS Privacy Working Group that concentrates, primarily their original charter was just between the stub and the recursive resolver, quickly followed by some privacy technologies like root loopback, then QNAME minimization. This minimizes the amount of data that's sent to an authoritative server. DNS over TLS, we start getting into DNS encryption. Then domain name cut. Once again, this is a technology that limits the amount of data that gets sent to the recursive. DNSSEC aggressive, same thing, reduces the amount. Then we have a Deprive rechartering to concentrate on the recursive to the authoritative, and that's the part that we're interested in. And finally, after 4 years, TLS 1.3 becomes a standard. and quickly followed by DOE. So DOE really had a very quick evolution, went from a draft to a standard in about a year. And then there's the Mozilla TRR, which isn't technically an IETF standard, but it's what Mozilla says that recursive resolvers have to comply to in order for them to communicate with them. So where do these things fit in the DNS ecosystem? Between the stub and the recursive, we have encryption technologies. And this is where a lot of the controversy is going on right now. And between the recursive and the authoritative, right now it's really minimization technologies. What I mean by minimizing is the information that's sent and the frequency that's sent to the authoritative servers. So we have recursive to authoritative encryption, which we're calling ADOT. It's not yet defined yet. It's a different set of problems than between the stub and recursive. And we're using ADOT to differentiate the path and the problem set between the recursive and the authoritative as between the stub to recursive, which I'd like to call RDOT. Any votes? All right. So now that we know what ADOT is, we've got, although it provides DNS encryption, it also provides a lot of other things that may threaten the stability of the authoritative servers that were otherwise designed to maybe optimize unencrypted DNS over UDP or TLS. So to mitigate those threats, I think we need to define the problem set, talk about potential next steps and suggestions. So this presentation is based off of a draft that I put together with Tim April and Jason Livingood, an IETF draft. It hasn't been adopted yet, largely because ADOT is not yet a defined protocol. So what are some of the things that it's missing? There's no way right now for a server to advertise whether it accepts a TLS connection, or in this case, a DNS over TLS connection. It's one of the missing pieces. Now, you could probe between the stub and recursive. That's a much smaller problem. Between the recursive and the authoritative, okay, I'm going to try to move along a little faster. It becomes a much bigger problem because you're talking with a lot of them. So let's move on. So another one of the problems is port 853. So one of the problems there is it's really susceptible to a quick downgrade attack. Let's say there's somebody in the middle, port 853, we say, okay, it's denied. So then we try port 53 over TCP, and all of a sudden it's downgraded and they can monitor it. Okay. Another question, what version of TLS should we consider? I think undoubtedly TLS 1.3. We have performance enhancements, we have security enhancements, and there isn't a large installed base right now that prevents us from doing this. So I'd say, yes, we should do this. Then going forward, should we consider resumption? Absolutely. You have connection efficiency, you have resource efficiency. Now, zero RTT, we may want to look at that just because that may be susceptible to not only replay, but side channel attacks. Something that, so operators will collect telemetry and data and packets looking for a packet of death, measure the performance and health of their infrastructure. This presents a problem if those packets are encrypted, and it further presents problems if we're using TLS 1.3 because that provides perfect forward secrecy. There's no global key to unlock everything. We also may want to segregate our services, keep our traditional UDP, DNS over UDP over TCP in a separate area. We might look at separating those using, let's say, layer 4 routing, where you could say everything to port 853 goes to one place, everything to 53 goes someplace else. We might consider for monitoring and attack mitigation different IP addresses, and we want to maybe weigh the pros and cons of UDP or of a a proxy server. So one quick gain would be socket efficiency. Now this is going to be different. There's no global one that can work for everyone. They're going to have to be tuned for each one, but we want to look at optimal persistent connections, optimal read-write buffer, session timeout, close wait time, and connection time. And again, that's going to have to be tuned for each individual case. We're deploying ADOT in a time when quantum computers are potentially reality. They have potentially a very long life, so it's only prudent that we consider quantum computing when we deploy this. One of our thoughts is using external pre-shared keys. TLS with a PSK extension and 1.3 could be a big enabler here. And finally, next steps, further studies. So unlike stub to recursive, authoritative servers affect users in ways that they can't really work around or avoid. So for instance, if all the authoritative servers for a particular zone are unavailable, that zone becomes unavailable. So we really have to, we're really insisting on having more empirical studies, so I'm really looking forward to Sheng Ho's presentation, see what's coming out there, because we need more empirical studies that look at a minimum at attack vectors, capacity planning, future footprint, traffic analysis, and we need to have these at internet scale, global studies that can help inform operators on the challenges and measurements that they're going to have to overcome in order to deploy this globally. So hopefully I made it in my 15 minutes. I apologize for speaking quickly.
Thank you, Carl. Any questions for Carl?
Petr Špaček, CZNIC. Do you have some considerations for like preventing the downgrade attack?
Preventing the, I'm sorry.
Have you thought about methods how to prevent the downgrade attack from happening on this channel? I mean, just curious whether it was part of the analysis or which is just not in slides or...
It's not. And one of the things I was thinking of, if we could have the precursor, in other words, some way of signaling the server capabilities, maybe we could use different ports for different destinations.
Yeah, definitely agree. Well,
if you have any thoughts, I'd be happy to hear them.
I think that this is the main problem which is stopping DPRI from like moving forward, because no one is willing to standardize protocol which is easily downgraded to plain text. But solving that is the hard problem. So, okay, anyway, thank you.
If you had a strict profile, you probably would never get an answer.
Yeah, if you have strict profile, you don't get to see most of the internet, so it's just no go. Thanks.
Sure.
Olur Guemerson, Cloudflare. Carl, thank you. That was very good. Comment on discovery mechanisms. Why not use TLSA records as a discovery mechanism?
Actually, that's something that we've thought about, and I'm waiting to hear more from the standards committees. In other words, these are considerations. We're not necessarily proposing one.
Okay.
I saw you mentioned RFC 7706 on one of your slides, the slides with all the arrows.
Yep.
Running a root zone on loopback or whatever, a local copy. Do you think, given the smallness of the root and the potential of being able to obtain a completely authentic version of it, that we would not necessarily need ADOT at the root?
Potentially. Again, we're really just putting it out considerations, so if that one actually holds, then great.
I'm specifically referring to publishing a zone MD record at the root and being able to get to authenticate all the DNS and all the unsigned records.
Yeah, I mean, there are problems with hyper-local loop and keeping things updated and whatnot. It's not something we're addressing specifically, but yeah, it would solve the problem to the root.
Good afternoon. Alan John from ICANN. I was wondering if you also looked at doing this not on TLS, but over QUIC directly, DNS over QUIC, and if you did, what's your thinking?
So at this point, we weren't addressing QUIC because I think ADOT is kind of, I mean, right now, TLS is a well-known standard. QUIC is still relatively new. I think from an operator standpoint, although it looks very attractive, I think I would be a little concerned putting a well-known protocol over a new protocol. I think that could offer a lot of other operational difficulties, but again, it looks exciting. It looks like there might be some huge gains there in the future.
So you will see DNS over TLS as a stepping stone to go maybe later to DNS over QUIC?
Sure, absolutely.
Okay.
Okay. Thank you very much, Carl. We come to the final presentation for this session, and that's Professor Shuang Hao. However, at the request of the speaker, this session is not going to be webcast. So we're going to end the webcast here. For the remote participants, we will resume at 4 o'clock local time. And are we ready? All right, so please welcome.